Okay, today in this video we're going to learn about something called definite integrals. In order to evaluate definite integrals, we'll need to use something called the Fundamental Theorem of Calculus. And once we learn, and Fundamental Theorem of Calculus has two parts. Part one lets us do our definite integrals. Part two lets us deal with our upper limit as a variable, which is called the second Fundamental Theorem of Calculus. We'll also learn the mean value theorem for integrals and something called the average value of a function over a closed interval. Let's start by defining a definite integral. Given that if f is continuous and non-negative on the closed interval from a to b, then the area of the region bounded by the graph of the function f, the x-axis, and the vertical lines formed at x equals a and x equals b is the area under the curve. And area is equal to the integral from a to b of f of x dx, where a is considered the lower bound of the integral and b is considered the upper bound of the integral. Okay, we're going to learn the different methods of doing this. We're going to learn different ways of finding area. First, we're going to using geometric formulas. So we're going to sketch a graph of this function and find the area using our knowledge of geometry. So we have our function is 4. So that means we have a vertical line at 4. And then we want to find the area under this curve and between this curve and the x-axis, starting at x equals 1 all the way to x equals 3. So I'm going to draw a vertical line at x equals 1. And another vertical line at x equals 3. And then between the area between those two lines, the x-axis and the equation 4. So this area here is what we're trying to find. That is a rectangle. So the area of a rectangle we know is simply length times width. So using our geometric formulas, we'll find area of this area under this curve by just taking the length, which is 2, times by the height of our rectangle, which is 4, which will give us 8. So the integral from 1 to 3 of 4 dx is equal to 8. Okay, let's do one more. I'm going to find the integral from negative 2 to 2 of the square root of 4 minus x squared dx. So I'm going to start by graphing the square root of 4 minus x squared, which is a semicircle whose center is at 0 and whose radius is 2. This curve here. And then I want to find the area under this curve into the x-axis, starting at negative 2 and going to 2. So it's this area of this semicircle. And we know the area of a circle is equal to pi r squared. So the area of a semicircle would be half of that. So 1/2 pi r squared. And our radius is 2 in this example because we go from the origin to our endpoint here. So we have 1/2 pi times 2 squared, which is 4. 4 times 4 divided by 2 gives us 2, so our answer is simply 2 pi. And that'll be the exact area under this curve. Okay, you try this one. Find the area from 0 to 3 of x plus 2 dx. First, start by graphing the line x plus 2. So that's a y-intercept of 2 and a slope of 1. So I'll go up 1 over 1, up 1 over 1 until I get to an x value of 3. And then I want to find the area under this curve until I get to the x-axis between the vertical lines at x equals 3 and x equals 0. So we have a trapezoid, and we know the area of a trapezoid is 1/2 base 1 plus base 2 divided by h. In this case, our height of our trapezoid is 3, and our base 1 has a length of 2, and our base 3 has a length of 5. So 2 plus 5 is 7, 7 times 3 is 21, 21 divided by a half is, or times by half is 21 halves. And that should have been your exact area. Okay, so this is how you find an area in a curve using geometry. Now we're going to learn a few properties so that we can start doing this algebraically. Our first property is that if we take the integral from a to b of f of x dx, so notice our upper bound and our lower bound are equal. They're the same value. Then our integral is 0 because we have not moved anywhere on the x-axis, so we have no area under the curve. Now, if I take the integral from a to b, where a is smaller than b, and if I'm going from a to b, where a is less than b, and then I take the integral of b minus a. So if my lower bound is greater than my upper bound, I have to do this following property. I would rewrite the integral as negative, or the opposite, of the integral from a to b of f of x dx. So in order to evaluate an integral, the lower bound must be lower or less than the upper bound. And we fix that by doing the opposite of the integral. Okay, if f is integratable on 3 closed intervals determined by a, b, and c, such that c is between a and b, Then the integral from a to b of f of x dx can be written as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So I can break up an integral at any point in the interior of the integral. That'll come in handy later on. The key is, notice that the upper bound of my first integral has to equal the lower bound of my second integral. And my my lower bound of my first integral has to equal the upper bound of my last integral. And that has to be equal to the original function. So let's, two more properties. F and g are integratable functions on the closed interval. So for one thing about integrals is we can factor out a constant. So the integral from a to b of a constant times f of x dx is the constant times the integral from a to b of f of x dx. Same thing with the sum or difference. We can break up that integral to have the integral from a to b of f of x dx plus or minus, depending if it's a sum or difference, of the integral from a to b of g of x plus dx. This comes very handy on doing the next type of problem. We're going to use geometry again to find the area under the curve from -6 to 18 of f of x dx. But notice I have multiple objects or shapes here to find the integral of. To find the integral from -6 to 18 of f of x dx, I need to break these up to three integrals. So my first shape is this semicircle, and it's only going from -6 to -2. So I would say this whole integral is equal to the integral from -6 to -2 of f of x dx, and that would represent the semicircle. Then I'm going to add the integral of the triangle, which I'm going to highlight here in red, and for the area under the curve, and that triangle is going to be from starting at x value of -2 going to an x value of 4 f of x dx. And then I'm going to add the area of this last triangle, which the calculus notation for that would be the integral from 4 to 18 of f of x dx. Okay, so we're going to start by finding the area of the semicircle. And remember, the formula for the area of a semicircle is 1/2 the area of a circle, which is pi r squared. So the orange area would be 1/2 pi times, and our radius for the semicircle is 2, which is equal to 2 pi. Now I'm going to find the area of the red section, but notice that the red is below the x-axis. Remember before I defined it by a non-negative integral, so that meant it needed to be above the x-axis? Well, how we fix this is we find we do the opposite of the area. So this would be minus the area under the curve. So any area under the curve we subtract. And so our formula is 1/2 base, which is 6, and height, which is 4. Working that out, I get 1/2 of 24, or minus 12. And then to find the area of the blue triangle, we are again above the x-axis, so it's positive. And that's area of a triangle is 1/2 base times height, so we figure out the length of our base. 18 minus 4 gives us 14. Times by the height of our triangle, which is 6. And the area of the blue triangle is simply 42. And then our final area of this object is 2 pi plus 30 when I take 42 minus 12. Okay, now we're going to find the integral from -1 to 1 of the absolute value of x. So we're going to start by graphing the graph of y equals absolute value of x, starting at -1 and ending at 1. So it's the V shape like this. And we're going to find the area under the curve. So the vertical line at x equals -1, and a vertical line at x equals 1, and under that curve into the x-axis. So these two areas is the area that we're going to find. So notice we have two integrals to do. The integral from -1 to 0, that should be 0, of the absolute value of d of x, plus the integral from 0 to 1 of the absolute value of x dx is equal to our original integral problem. And so that is a triangle, so it's 1/2 base times height, and the same area for the other triangle, which is simply 1/2 plus 1/2, or equal to 1. So the area so the integral from -1 to 1 of absolute value of x is 1. Right, now we're going to find the integral from pi to pi of sine of x dx. So first thing that screams at me is notice that my lower bound and my upper bound are the same. Anytime the upper and lower bounds are the same, our integral is 0. Okay, you try this one. First thing you need to notice about this problem is that the lower bound is larger than the upper bound, so we first need to negate it and do the opposite of the integral from 0 to 3 of x plus 2 dx. So I'm going to start by drawing my graph of x plus 2, which we've done earlier. So we have an x-intercept of 2 and a slope of 1. And we want to find that area from 0 to 3. So we got a vertical line at x equals 0 and at x equals 3. And so area under that curve into the x-axis. This is the area that we want to find. And so that's by a trapezoid. So bring down that negative sign. And remember, our area of a trapezoid is 1/2 base, height, times the sum of the bases, which we call is 21/2. So our answer here is going to be negative 21/2 because we went in the other direction. Now we're going to evaluate the integral from 1 to 3 of this function using our properties. So first thing I notice is I can break it up using my sum or difference property and have the integral from 1 to 3 of negative x squared dx plus the integral from 1 to 3 of 4x dx minus the integral or plus the integral of negative 3 dx or minus the integral from 1 to 3 of 3 dx. I find it easier if I take the negative out now, but it does not matter what you choose. Okay. Then I notice that I can use my constant multiple rule and bring the constants out. So it comes negative 1 times the integral from 1 to 3 of x squared dx plus 4 times the integral to 1 to 3 of x dx minus 3 the integral of 1 to 3 of dx. All right. Then using the given information, the integral of 1 to 3 of x squared was given to us to be 26/3. So we're going to substitute that in place of this integral notation. Plus 4, and then replacing the integral from 1 to 3 of x dx with what it was given to be equaled, which is 4. Substitute that in. Minus 3 times the integral from 1 to 3 of dx, which was given to us to be equal to 2. So replace that value with 2. And then we just simplify this down. So we get negative 26/3 plus 16 minus 6, which is negative 26/3 plus 10, which can be written as 30/3. And our final answer would be simply 4/3, would be the area under this curve. And now we're finally ready to use the Fundamental Theorem of Calculus. There are 2 parts to the Fundamental Theorem of Calculus, which can be abbreviated as f of tc. Now the condition that needs to be met first is that the function f must be continuous on the closed interval from a to b. Then if big F is the antiderivative of little f, then the integral from a to b of f of x dx is equal to big F evaluated at b minus big F evaluated at a. So the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. That's it. That's the Fundamental Theorem of Calculus. So if I want to find the integral from 1 to 3 of x squared minus 3 dx, I'm going to find the antiderivative, which is 1/3 x cubed minus 3x, and evaluate that from 1 to 2. So I substitute in my upper bound first, substitute 2 in, then subtract, substituting 1 into my antiderivative. All right, when I simplify the left-hand side, I end up with 8/3 minus 6. And then I'm going to just distribute this negative here. And then 1/3 minus 3, which I can write as 9/3. So 8/3 minus 18/3 gives us negative 10/3. And 1/3 minus 9/3 is 8/3, so minus a minus becomes positive, so our answer is negative 2/3. We've actually found the area of this curve algebraically. Absolute value rules, remember when we found the derivative of absolute value, we first had to rewrite it as integral, as a piecewise function. Same thing when we found the limit of absolute values. So the same rule applies when you find the integrals of absolute value functions. Your first step is to rewrite that absolute value function as a piecewise function. So I'm going to be negative 2x plus 1 if I distribute that negative through. When x is less than or equal to, remember to find the value where it breaks up, you set the ends, whatever's inside the absolute value equal to 0 and solve, and I get 1/2. And then I'm going to use x squared minus 1 whenever x is greater than or equal to 1/2. So since 1/2 is between our upper and lower bounds of this integral, we have to break up the integral from 0 to 1/2 of our top equation, since that's less than 1/2. So that'd be negative 2x plus 1 dx, plus the integral from 1/2 all the way to 2 of our second equation, which is x squared minus 1 dx. So we're going to start by finding the antiderivative of negative 2x plus 1. Which is negative x squared plus x, evaluated from 0 to 1/2, plus the antiderivative of 2x minus 1 is x squared minus x, evaluated from 1/2 to 2. So remember Fundamental Theorem of Calculus, we evaluate the function at the upper bound, so I'm going to replace every x with 1/2. And then subtract, replacing every x with 0. And that takes care of first one. Now plus, again, I'm going to evaluate the upper bound of 2, so replace every x with 2, minus replacing every x with 1/2. Simplifying this down, plus 2 squared is 4 minus 2 minus 1/4 plus 1/2. Combining all like terms, negative 1/4 plus 2/4 is positive 1/4 minus another 1/4. Those cancel out. Then I'm left with 4 minus 2, which is 2, plus 1/2, which is 5/2. Okay, you try this trig one. Recall that the antiderivative of secant squared x dx is tangent of x. So the integral from 0 to pi over 4 of secant squared x dx is the tangent of x evaluated from 0 to pi over 4. So that becomes the tangent at pi over 4 minus the tangent at 0. Recall from a unit circle, the tangent at pi over 4 is 1, and the tangent at 0 is 0. 1 minus 0 is 1. All right, before I can find the antiderivative of 3 to the square root of x, I need to rewrite this as 3 times x to the 1/2 power. Then I can use my power rule, and I can find my antiderivative to be 3 times 1/2, x to the 3/2 times 2/3. Evaluate it from 1 to 4, and then that simplifies down to 2x to the 3/2. Evaluate it from 1 to 4, so plugging in 4 minus substituting in 1. Okay, now remember, the 4 to the 3/2 is the same as 4 times the square root of 4, which is simply 16 minus 2, which is 14. Okay, we're going to find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis and vertical line 0 and 2. So the calculus notation for that entire sentence is simply the integral from 0 to 2 of 2x squared minus 3x plus 2 dx. So that's what we want to figure out. So we have to translate that into a calculus notation, and then we're just going to do the process using the Fundamental Theorem of Calculus. So we're going to find the antiderivative of this polynomial. And we end up with 2/3 x cubed minus 3/2 x squared plus 2x, evaluated from 0 to 2, which means I need to first substitute in 2 into my polynomial, my antiderivative, and take that result minus substituting in 0. And that gives us 16 minus 6. This should be plus 4. Notice I somehow changed that plus 2x to plus to minus. Let's fix that. And that gives us 16/3 minus 6/3, which is simply 10/3. Okay, now we're going to find the mean value theorem for integrals. Before I find the mean value theorem for integrals, recall our mean value theorem for derivatives. Remember, derivatives focused on the slope of the tangent line. So the mean value theorem for derivatives was simply the slope of the tangent line equals the slope of the secant line, which in notation was f prime of c is equal to f of b minus f of a over b minus a. To find the mean value theorem for integrals, again, the function f has to be continuous of the closed interval from a to b, and that there exists some number c on the closed interval such that the area under the curve, and if I pick the c value at the right spot, it will, if I formed a rectangle through the c value, that area of that rectangle will equal the exact area under the curve. So this specially chosen c value, the area under the curve is equal to the area of the rectangle. So let me kind of give you an example of what this looks like. So let's say this is our function f of x. And I wanted to find use the mean value theorem of integrals. So let's say I'm over the interval from a to b. I know by the mean value theorem there must be some value c at some point on this interval, we'll say if c is here, such that if I drew a rectangle through point c, beginning and ending at A and B, so this would be this area. That area, this purple area here formed in that rectangle, will be exactly the same as the area under the curve. And the area under the curve is the integral from a to b of our f of x dx. So the height of this rectangle is f of c. The width is b minus a. All right, it's the traction of our endpoints. That formula there is length times width, or the area of the rectangle at that value c, and that is equal to the area under the curve from a to b, which is the integral from a to b of f of x dx. This is your mean value theorem for integrals formula. And it's saying that if the purple area and this red area are equivalent at some value c somewhere in that interval. And then, of course, we'll be working on finding that c value. So what I've just highlighted in the yellow is our interval, our mean value theorem of calculus. Okay, find the value or values of c guaranteed by the mean value theorem for integrals for the function over the given interval. So for the function f of x equals x squared, from the interval from 0 to 3. So remember, mean value theorem, area under the curve equals area of that special rectangle at c. So area of the curve is from 0 to 3 of x, the square root of x dx, and that's equal to our function value at c times our b minus a, which is 3 minus 0 in this case. So I would start by rewriting the square root of x as x to the 1/2, so I can use my power rule to find the antiderivative. And then the antiderivative of x to the 1/2 is 2/3 x to the 3/2, evaluated from 0 to 3. And then, so remember, to evaluate using Fundamental Theorem of Calculus, I plug in the upper limit minus the lower limit, the lower bound. And then the cube root of 3 squared is 3 times the square root of 3, times by that 2/3, minus 0, which would be 2 the square root of 3, is the area under the exact area in the curve. This is equal to f of c. Well, f of c is our function evaluated at c, or the square root of x in this case, square root of c in this case, times by 3 minus 0, which is 3. So I know this 2 the square root of 3 is equal to 3 the square root of c. So I just solve this equation for c. So I'm going to start by dividing 3 by each side. And then the opposite of square rooting is squaring each side. And so I end up with 4 times 3 over 9 is equal to c, which is 12/9, which simplifies down to 4/3. So c would have to be at the point 4/3. You try the next one. So the area under the curve is represented by the integral from 1 to 3 of 9x to the negative 3 dx, and that's equal to f of c evaluated from 3 minus 1. F of c I can rewrite as 9 over c squared, and then the antiderivative of 9x to the negative 3 is 9 times negative 1/2 x to the negative 2, evaluated from 1 to 3. So that gives us 9 divided by 2x squared, evaluated from 1 to 3. So that gives us negative 9, evaluating at 3, divided by 2 times 3 squared, minus a negative, so it becomes positive 9 of 2 times 1 squared. Simplifies down to negative 1/2 plus 9/2. Negative 1/2 plus 9/2 is 8/2, which is 4. F of c is 9 over c cubed, minus times by 2, which is simply 18 over c cubed. To solve for c, I would multiply each side by c cubed to get 4c cubed is equal to 18. Divide each side by 4, get c cubed is equal to 18/4, which simplifies down to 9/2. And then take the cube root of each side. So c is simply the cube root of 9/2, and you can leave it like that. Our next theorem is called the average value function. Average value of a function. If f is an integral on the closed interval from a to b, then the average value of f on the integral is found by taking 1 divided by b minus a of f of a, the integral from a to b of f of x dx. Okay, what's really cool, the average value is just the y value of that special rectangle that we talked about in the mean value theorem. So actually, this formula is the mean value theorem just rewritten. And I'll show you how it's done. So remember, our mean value theorem for integrals was the integral from a to b of f of x dx is equal to f of c times b minus a. Well, if I divided each side of this equation by b minus a, I get 1 over b minus a is times by the integral from a to b of f of x dx is equal to f of c. F of c is the function, is the average value of the function. So this average value of the formula, that is f of c. That's what we call it. So when it asks you to find the average value of the function, it asks you to find the y of that special rectangle, that y, or the height of that special rectangle. Whereas when we're doing the mean value theorem, we're finding our x, where the special rectangle is drawn from. So they're very closely related. So we're going to find the values of the function over which the average value of the function for these intervals. So we're going to start with this. So remember, that's going to be 1 minus b times b minus a of the integral from a to b of f of x dx. That's our average value formula. So in this case, b is 3, a is 1, and our f of x is this function. All right, so 3 minus 1 is 2, so I got 1/2 the integral from 1 to 3, and I need to simplify this integral because remember, there's no quotient rule for integration. So I cannot evaluate the integral as written, so we need to do a little simplifying first. So I'm going to distribute the 4 to get rid of the parentheses on the top, and then I'm going to break up the fraction and simplify. So 4x squared divided by x squared is just 4, and 4 divided by x squared is 4x to the negative 2. Now I can find the antiderivative. So the antiderivative is 4x plus 4 times negative x to the negative 1, evaluate it from 1 to 3. Or if I write that in simplified form, we have 1/2 times 4x minus 4 over x, evaluate it from 1 to 3. So to evaluate this integral, I need to substitute in place of every x 3, minus substitute in place of every x 1. And I have 1/2, let's start in the parentheses first, that gives us 12 minus 4/3, minus 4 plus 4, distributing the negative, minus 4 plus 4 cancel out. And so I'm left with 12 minus 4/3. I can rewrite 12 as 36/3. Minusing the 4/3 gives us 32/3. 1/2 of 32/3 is simply 16/3. You try this next one. Find the average value of the function on the interval from 1 to 4. So the integral from 1 divided by 4 minus 1 times the integral from 1 to 4 of 3x squared minus 2x dx is 1/3 of the integral from 1 to 4. And the integral from 1 to 4, using my antiderivative or integration process, gives us 1/3 times x cubed minus x squared, evaluated from 1 to 4. So that means I'm going to substitute in, using my Fundamental Theorem of Calculus, part 1, 4 in place of every x, minus substituting in 1 in place of every x. So I have 1/3 times, 4 cubed is 64, minus 4 squared, which is 16, so 64 minus 16. Distributing the negative here, we got negative 1 plus 1, so then 1's cancel out. We're left for 64 minus 16, which is 48, divided by 3, which is 16. Okay. Last but not least, we're going to learn the Fundamental Theorem of Calculus, Part 2, or sometimes called the second Fundamental Theorem of Calculus. So the Fundamental Theorem of Calculus, Part 2, involves when the upper bound is a variable. So our definite integral that we've learned so far is the integral from a to b of f of x dx, where a is the lower bound and the upper bound are constants. The lower bound is smaller than the upper bound. And then the function f of x is a function of the x variable. Whereas the Fundamental Theorem of Calculus Part 2 has us deal with the integral from a to a variable, which is from a to x, of f of t dt, where t is considered a dummy variable. The key is that variable cannot be the same variable as our variable in the upper bound. So our lower bound has to be a constant. It can be any number, but it must be a constant. And the upper bound must be a variable, and it must be a singular variable. X, y, z. Cannot be x squared. Cannot be 3 times x. It has to just be a variable. And then inside here is the function. F is a function of t, or f is a function of the dummy variable. And you can randomly choose that variable. It's just tradition is to choose t if t is not already used. Okay, so what is the Fundamental Theorem of Calculus Part 2? So Fundamental Theorem of Calculus doesn't let us evaluate this integral from a to x, but it lets us find the derivative of the integral from a to x of f of x dx. So if I wanted to find the derivative of the integral of a to x of f of t dt, that's simply equal to f of x. F evaluated up the upper bound. Now, if the upper bound is just a singular variable, it fits this formula perfectly. So that's what example A is. And it's going to be the easiest one to do. But again, notice that the lower bound must be a constant, the upper bound must be a singular variable, one variable by itself. Okay, so use the second fundamental theorem of calculus to find the derivative of the antiderivative of f of x. So big F prime of x is equal to the derivative of 0 to x of the square root of t squared plus 1 dt. Now, since I'm finding the derivative of the integral and the upper bound is a variable, that is just simply equal to the square root of x squared plus 1. I just replace the variable with, place the t, the dummy variable, with the x, the upper bound. Now, when the upper bound is not a singular variable, it's not x, we have to substitute in another variable in its place, and then we have to apply the chain rule that we learned with derivatives when we find the derivative of this. So we must apply the chain rule. Okay, so how you do this? First, you must rewrite this so that the upper bound is a singular variable. So I'm going to replace that x cubed with another variable. I'm going to use u. So I'm going to let u equal x cubed. And remember, with our chain rule, when we take a derivative of something, we have to times it by the derivative of u to the x. So if I rewrite our f of x, big F of x, as the integral from pi over 2 of x cubed, I rewrite big F of x as the integral from x over 2 of u times of the cosine of t dt. Now I have a singular variable in the denominator, in the upper bound. So I can apply the Fundamental Theorem of Calculus Part 2. And the Fundamental Theorem of Calculus Part 2 says if I want to find the derivative of this integral, that is equal to simply, to find that derivative of that integral, it is cosine u times by the derivative of u, which we found to be 3x squared. So rewriting that is 3x squared cosine, and u is x cubed. So the derivative of this integral using the second fundamental theorem of calculus is 3x squared times cosine of x cubed.